So Harsh, can you see this PPT?
Yes, sir.
Okay. So let us start. So first I'll give you a very brief uh, introduction to the physical storage structure, which I think you have already got introduced if you were taking the operating systems course in this semester also, or to take in the next semester, I don't know, maybe in the next semester or previous semester. So I'll give a brief description only of physical storage system, specifically the disk structure. The secondary storage system is the disk space. So this is the basic structure of a disk. As you know, many of you know that these are the platters, okay, circular plates. So there are multiple platters which rotate on a spindle. This axis is called a spindle, and both of the surfaces of a platter, okay, are magnetic coated. That means that can record data. Both side of platter can record data. Now, if you look into one surface, any one surface of a platter, then you can see these concentric circles are known as tracks. For example, this one is a track. Similarly, there are multiple such concentric tracks on a specific side of a platter. And then you can see that each of the tracks is divided into the smaller units which are called sectors. But remember that these tracks and sectors, these are logical divisions only. There is no such physical division. This is a continuous surface on both sides of the platter. But logically, we divide into number of tracks from the center towards the perimeter, and each of the track is divided into number of sectors. Okay. Now this is the head. This is called the arm, and the attached to the arm, you can see there are two heads connected to the arm. The heads can read the upper surface or the lower surface of a platter. So this is the arm head, and when you place the arm head on the top of a sector, it can read the data from that particular sector. So in order to read a specific sector, what is needed? Two things are needed. One thing is that the platter should rotate. The first thing is that the arm should be moved. Arm can move in this direction, that is horizontally. It can move from the center towards the radius, and that means the innermost track to the outermost track it can move, whereas this can circularly rotate the platters. Actually, the platters and the spindle rotates continuously. The spindle rotates continuously. Only the arm is moved according to the request. That means which sector you want to read, according to that the arm is moved. So in order to read a particular sector, you have to move the arm. Hello.
Yes, sir.
So you have to move the arm on the top of that sector. This is called arm seeking. You are seeking the arm. Okay. So this is the basic thing. So ask me questions whenever you face any difficulty in understanding. And another term you can see here, cylinder. What is a cylinder? the collection of all the tracks with same index. For example, if this is the third innermost track in this platter, then the third innermost tracks on all the platters on both the sides, the collection of all such tracks is called as cylinder. So that means in order to read any sector on a specific cylinder, you don't have to move the arm. The arm can be placed on that particular cylinder, and then you can read all the sectors of all the platters on both the sides of the platters. Okay, these things I have explained. What is a read-write head, track, sector, cylinder. Disk controller, I think already you have also got introduced in the operating system course. So it is a device controller. That means it has a processing unit like the CPU, its own RAM memory, primary memory, and then it can execute some commands, your machine level instructions. So those commands are received from the main CPU, the operating system device driver program that controls the device controller. So it sends the commands and the disk controller interprets those commands. For example, if you give a command to read a particular sector, then the disk controller moves the arm to the specific cylinder and then reads the data from that particular sector or sectors through the arm head and collects it inside its buffer and then notifies to the CPU. The rest of the things you know in the operating system, then on IO is done from the buffer of the disk controller to the main memory. So this is this and checksum along with every sector, the disk controller also maintains the checksums corresponding to that sector. So which is something like an error correction, error checking code. So if somehow accidentally some bits of the data gets corrupted, then with a high probability the checksum will not match, and then that is detected as a bad sector. So performance measures of a disk you when you use a particular disk or when you purchase a disk, how do you measure the performance of that disk? There are certain parameters. So basically all the parameters are related to some delays. So what are the delays? First is access time and the second one is data transfer time. Access time and data transfer time. These are the two basic parameters through which we should evaluate the efficiency of a disk. Access time meaning when you give a request, you meaning again the same thing, device driver program from the CPU. It gives a command to read the data. Now, when you issue the command to the point when the data transfer starts, that time is called access time. And the remaining time, that means actual transfer of the data from those sectors, is called data transfer rate. So as you can understand, then access time basically involves the seek time and the rotational latency. How much time it takes to move the arm from its current position to the desired position, the top of the desired track, or in other words, you can say on the top of the cylinder. And rotational latency, how much time it takes to rotate the cylinder or the track under the head of the arm. So these are the two things. So when we evaluate any disk scheduling policy algorithm, we only measure the seek time. We do not measure the rotational latency. Why? Because as I said, the spindle is rotating continuously. So your algorithm does not have any impact on the rotational latency. It is only decided by the manufacturer, meaning whatever you have purchased according to that, it has some RPM, rotation per minute. So you do not have control over that. It is continuously rotating. But your algorithm can have an impact on the seek time, because how many seeks you are doing. Meaning, if you have an optimized algorithm, you may need a minimum number of seeks, meaning arm movements, to read your data. However, if you have a bad algorithm, then more number of arm movements, seeks, will be required. Time required for one particular seek is constant, because that is decided by the hardware, physical hardware. But number of seeks is definitely decided by your algorithm. Now, what is a block? That you already also know. I think that is the smallest unit of storage allocation. I think if you have studied the operating system course, then you are familiar with the concept of pages. So usually the size of a block is same as the size of a page. So one block, size of one block can be equal to size of one sector or more than one sectors. But it is in multiple of sectors, meaning, and second thing is that successive sectors, contiguous sectors, if contiguous sectors are not available on the same track, then sectors are allocated from the same cylinder at least, so that you can read all the sectors corresponding to a specific block without moving the arm. Meaning once you move the arm to the beginning of the block, then later the probability that you need to move the arm is negligible, because this scheduling is done in that way. We try to, that means the disk management algorithm tries to allocate sectors from the same cylinder, or at the worst case, when it is not available, then it allocates from the nearby tracks. So that is a block. Usually the size of a block is from 4 kilobyte to 16 kilobyte, and the size of a sector is usually 512 bytes. Sequential access pattern and random access pattern, which I already just explained just now, that if you have a bad algorithm, then you can request for blocks or sectors which are not consecutive. That is random access pattern. That means your successive requests are from any random track. However, if you have a sequential access pattern, then it is expected that successive requests are from the successive blocks. That means from the same track, and then from the nearby track, and then from the nearby track, etc. So that the only objective is that the arm movement is optimized. Okay. This is the basic background required. If you have any question on whatever I have discussed so far, you may ask. Otherwise, we will move to the main topic that we'll discuss today, is query processing. So this background is required for regarding the physical structure, disk structure. Now we'll go to query processing. So this is the basic flowchart. How, when you execute a query, for example, if you execute a query, select something, select salary from employee where age is greater than 30, some query like that, select from where. How is it executed by the database system? So the first step is that the query is submitted to an algorithm called a parser. This parser is something like a translator it translates the query from one language to another language. The input is in SQL language. Select from where, group by, etc. The SQL that you have already learned. And the output of the parser is in relational algebra expression. Sigma, pi, these things which you have already learned in relational algebra chapter. So the input is select from where, the output is sigma, pi, etc., etc. in the relational algebra form. That translation is done by the program called parser. Like you have seen in your C programming operating system also, that source code is C code, and then the compiler translates it into an object code, which is usually fast machine readable code, and then at the next level it is binary, similar to that. Now, next step, this relational algebra expression is then submitted to another program called optimizer. What this optimizer does, one relational algebra expression can be evaluated in different ways. There are many different ways to evaluate one particular relational algebra expression. Now let me explain to you what do I mean by that. So let's suppose we have a query, select as I said, salary from employee where age is greater than 30. So first we translated. Now you can translate. So first step, as I said, you can translate. You have to translate it into the relational algebra expression. So it can be sigma age greater than 30 from employee and then project the salaries. Or you can do what? You can do project salary and age from employee first and then apply the condition select age greater than 30 and then finally project salary. So this will also give you a correct answer. This will also give you a correct answer. Right? There is no doubt that both of the queries will give you the correct answer. But if I ask you, maybe most of you are thinking that why should I do it in this way? This is much simpler. Can any one of you tell me what is the advantage of doing it in this way? Can you guess? The point is, see, when before applying the selection condition, what is the input relation? Here, the original relation you are taking. But here, you are taking only two columns of the original relation. That means the output is the length. So if there are 1,000 records here, then after applying the project operation, there will be 1,000 records. So the the height will remain the same of the tables, the original table, and after applying the projection. have to main memory, number of block transfers you're doing is you have, and of course, so when the main table is containing suppose 1,000 blocks and the index table if it contains only 100 blocks or 10 blocks, then searching, which is a linear search, so through the file on the main table or main file is much more time consuming than searching in the index. These things already discussed in the indexing chapter, I think. So similar logic arguments can be placed here that when you take the original relation, the size is very large number of blocks. But when you take the output of this, that means when you project only 2 rows, then definitely it will result in a much smaller file containing much lesser number of blocks. So now the next step is to apply a selection condition. Apply a selection condition. How can you do this thing? Suppose you don't have any index available for the file or the relation. You do not have any index available. Then the only option is that you have to linearly scan through the file. So if you would have executed this thing, then you needed to require to scan this file. However, here you need to scan only this file. So the cost of this is much lesser than the cost of this. So this is just an example that given a query written in uniquely written in SQL, we can have multiple interpretations in relational algebra term. These are called equivalent expressions actually, because the result of the expression when you execute are same, although the cost may be different. Execution cost, remember the cost does not only involves the execution time in the CPU, rather that is the negligible part. But the main thing is number of block IOs that you need to do in terms of that. So total execution cost may be different, but the result is same. Those relational algebra expressions are called equivalent expressions. Now, second thing is that inside a relational algebra expression, for example, this is a relational algebra expression, this is a relational algebra expression. We have several operations. So sigma select is an operation, pi project is an operation, selection is an operation, projection is an operation, join is an operation, basic operations. Then aggregate function is an operation, union is an operation, intersection, Cartesian product, all these are operations. Some operations are unary, some operations are binary, takes one relation, takes two relations, etc. These operations, basic operations, definitely how do you implement that operation? For that also you need some algorithm. For example, sigma, even if I consider the simplest one, suppose sigma A is equal to V from R. R is a relation and A is an attribute on that R and V is a value. So how do you evaluate this thing? You need an algorithm which will take R as the one of the inputs and V another input, and then it will give you the output, another relation, resultant relation. Fine. How do you do that? So you require an algorithm. Now, what algorithm to use? Is there any one algorithm? No. The answer is no. There are multiple algorithms available to implement sigma. You have algorithm A1, A2, A3, like you have studied in operating system that there are multiple CPU scheduling algorithms, memory management algorithms. In computer networks, you have studied there are multiple routing algorithms. Similarly, in order to implement sigma, you have multiple options available and none is universally optimal. None of the algorithms are universally optimal. That means you cannot say that A1 is the best in all situations. A1 is best in some scenarios, A2 is best in some other scenarios, whereas A3 is best in some other scenarios. Similarly, in order to implement, there are multiple algorithms available. In order to implement join, there are multiple algorithms available, etc., etc. So finally, and definitely, you have to choose the algorithm which is optimal for your scenario. Scenario meaning basically it depends on the statistics of the data. The data on which you want to apply your operations, they must have, this is some kind of a metadata, you can say. For example, how many rows are there in the relation, how many columns are there in the relation, how many unique values are there for a specific attribute. So these are kind of metadata, data about data, and which are kept and maintained by a database system in a file known as database catalog. Okay, in a database catalog, the database system maintains all these statistics regarding all the relations maintained by that database. So from that statistics, we can decide whether A1 will be optimal or A2 will be optimal or A3 will be optimal in order to implement the sigma operation on those relation or relations. Depending on that, we choose the algorithm. Okay. So there are two things. When you translate a SQL query into relational algebra expression, there can be multiple equivalent expressions. So first thing, you have to choose the algorithm, expression with the lowest cost, meaning which one has the optimal cost. Second thing, you have to choose algorithms for each of the operations in an optimal way also. These two things are there. So that is the task of the optimizer. That's why it is shown that the optimizer takes the relational algebra expression. When you translate, you generate only one relational algebra expression by the parser. But then the optimizer explores that particular relational algebra expression to see how many equivalent expressions can be generated, and if I take the optimal algorithms for each of those equivalent expressions, then what would be the cost? And in order to do that, it needs data about data, statistics about the data tables, as I said. And then finally, it produces something which is known as an execution plan. So what is an execution plan? Execution plan is nothing but an annotated relational algebra expression. So annotated relational algebra expression, meaning it is a relational algebra expression where for every operation in that expression, it is clearly mentioned which algorithm you have to use. That means when you are generating the expression, that means you have decided that, okay, this is the final optimal expression that I have to evaluate. And at the same time, you have decided which algorithms to use for the specific operations in that expression. So that is called an execution plan. And finally, the execution plan is submitted to evaluation engine. The evaluation engine takes the execution plan and takes the actual data, the tables, and then runs the algorithms as mentioned in the execution plan on the data and generates the output. So this is the complete flowchart that when you submit a query, what are the steps that the database system executes to generate your output. Up to this point, anyone, if you have any questions, you can ask me first, then we can proceed. Okay. Next. Now we'll see some of the basic operations. As I said that there are multiple algorithms available to implement basic algorithms, selection, projection, join, etc. What are those algorithms? In order to just get a flavor of what I explained so far, that I'll give you some examples of algorithms which can be used in order to implement the same operation. For example, in order to implement the selection operation on a particular table, how many possible algorithms we have and what are the costs? How can we estimate the cost of applying those algorithms on a particular table? That we'll see. So in order to implement, so first is the selection operation. In order to implement a selection operation, as I have said that the easiest way, easiest in the sense the algorithm is easiest, not in terms of cost. Easiest way to implement is to do a linear search. You have to linearly scan from the beginning of the file to the end of the file. File meaning file containing the data relation, to see which records are satisfying the selection condition. Now, let us try to estimate the cost associated with this algorithm. Okay, how would we evaluate the cost? We would evaluate the cost in two terms. In terms of the number of block transfers that would be required, number of blocks that we would require to transfer from the disk to the main memory. And second thing, number of SICs. What is the SIC? Arm movements. That arm I have shown just now. How many arm movements SICs will be required? These are the two factors. Okay. Now, as I have said that one block transfer, how much time it takes to do one block transfer? So that may be, suppose TT. T of T is the time to transfer one particular block, and TS is the time for one SIC, one arm movement. So if we can calculate how many block transfers will be required, say B, and how many SICs will be required, say S, then the total time required to perform that operation is equal to B into TT plus S into TS. Clear? Now for the linear search, how many block transfers will be required and how many SICs will be required? Let us consider first the worst case scenario. In the worst case, how many block transfers will be required? And so it depends on the condition, the selection condition, on which attribute you are applying the condition. It may be a key attribute, meaning a candidate key, or it may not be a non-key attribute. So what is the difference between a key attribute and a non-key attribute? If it is a key attribute, then there will be only one row satisfying that condition. Meaning if we are checking an equality condition, condition can be again of two types: equality and inequality. Greater than equal to, less than equal to, these are inequalities, and equality, equal to. So equality condition, definitely if it is a key attribute, then only one row will satisfy, one record will satisfy that condition. Otherwise, there may be multiple records. So you have to scan through the entire file. Definitely, then you have to access BR number of blocks from the file, where BR denotes the total number of blocks containing the records of the relation R. Because you have to access the entire relation, there is no other way. So if the relation is stored in BR number of blocks, since you have started already indexing, that you already know what are blocks of a relation. So all the blocks, BR number of blocks holding the relation, you have to access. So number of block transfers required is equal to BR. Now, if it is a key attribute, in the second case, when it is a key attribute, we know that one record only will satisfy the condition. So as soon as you have found that particular record, you can stop the search. You do not need to process the rest of the file further. So the point is, average case, when would you get the record? So definitely we would require to scan half of the file on an average, because the best case is that the first one matches and the worst case is that the last one matches. So the average is that half of the blocks you have to access on an average if it is a key attribute. So BR by 2 block transfers will be required. And how many seeks will be required? Arm movements will be required. Now see, in order to read a particular relation, we first need to set the arm head on the top of the first block of the relation. We need to set the arm on the first block of the relation. You have to seek the arm to the first block of the relation. But in order to read the consecutive blocks, you do not need to move the arm further. Why? I have already explained while discussing the physical storage structure that we need, most of the time the disk management system allocates consecutive blocks when it allocates a file. And if consecutive meaning maybe consecutive in the same track or from the tracks of the same cylinder, so that you do not need to move the arm, or when no block is available on the same cylinder, it gives from the nearby tracks. So that's why we assume that when you are reading a file, you need to only set the arm at the beginning of the file. So one seek is required. And then in order to read the successive blocks, you do not need to move again the blocks, the arm head to the beginning of the other blocks. You do not need. Only the platter will rotate and the arm position remains the same and it reads the successive blocks. It is assumed. Why? I have explained. Okay, fine. But remember here one point, that in between, meaning suppose you have read the first block of the data file. Suppose this is the file or the relation, the blocks of the relation containing blocks of the relation. Now you have moved the arm head here and then you read the first block to the RAM. Then when you are working on that first block, you needed some other data from some other location of the hard disk, and then the head moved to that position. Then definitely when you have finished processing the first block, then you will require the second block. If you are doing a linear search type of thing, then you will require the second block And in order to read the second block, again a disk seek will be required, because now the arm head has been moved from that position to this position. I think I could explain what I'm saying. I'm repeating again. In order to read the first block, you said the you have seeked the head to this position. Then you read this block into RAM. Then while processing the data kept inside this block, you needed some other data which is located in some other position of the disk. So you moved the arm head to that particular position. So now you will require to reset it again to read the second block. So that means in between, what I'm saying, when you are working with B1, if you have moved it, so how many total seeks will be required then? Then if there are total BR number of blocks, then BR number of seeks will be required. So remember this point. Okay. Two scenarios: when you are reading the file consecutively, the blocks, and you are not moving the arm anywhere else, arm head, then you will require only one seek. But if you are bound to move this arm head into other locations, why you should move? I am giving one example. Suppose this is relation R and this is relation S. Now when you are doing a selection operation, then you may not need to move it to other location. But suppose you are doing a join operation, then definitely after taking the first block from R, you will require the data from the S also. So there is a necessity, it is mandatory that you have to move to the first block of the S also. So in that case, when you want again the second block, you have to do another move. Okay. So if this is not the scenario, then only one seek is required. But if this is the scenario, then BR number of blocks will be seeks will be required in order to read the entire relation. Is there any doubt? Fine. So linear search can be applied. The advantage of linear search is that linear search can be applied on any relation, whether it is sorted or unsorted does not matter. Linear search can be applied on any condition, whether it is an equality condition or inequality condition does not matter. Linear search can be applied whether there exists an index, hash or not, that does not matter. Or you are doing it on a primary key or candidate key or non-key, that also does not matter. But when suppose you already have an index available on some table or hash table available for some relation, then definitely it would be advantageous to use some other algorithm than linear search. So now we'll discuss some of those algorithms where we assume that an index exists on the input relation. So the first algorithm is A2, says that we have a primary index, which is sometimes also called clustering index, and we have to check the selection condition on a key attribute. Okay, and A3 you can see the same thing. There is a primary index and we have to check the condition on a non-key attribute, and the conditions are, in both cases, the conditions are equality checking. Okay, so let us analyze how can we do this thing. So the index, here one thing you have to mention, that they are assuming that the index is in the form of a B plus tree, which has been taught to you already. So as you know, the pointers to the actual data records are only in the leaf nodes of a B plus tree. That is the difference between B tree and B plus tree. So the pointer to the records, actual records, are only in the leaf nodes. So that means if we know that the height of the B plus tree is hi, this hi, height of the B plus tree is hi, then in order to reach to a leaf node, you have to do hi number of block transfers, because as you know that the linked list is implemented in a B plus tree is implemented in a linked list format. So the memories are allocated randomly from different locations of the disk. That's why in order to access every node of the B plus tree, you need to have one IO from the disk. So that means if you have to traverse from the root of the tree, B plus tree, to the leaf node, any leaf node, you have to do hi number of block IOs, block transfers from the disk to the main memory. And not only that, you need to do hi number of seeks also, arm movements also, because the blocks are scattered here and there in the disk, because they are done in a dynamic fashion as it is done for a linked list, any linked list. They are created dynamically. So that's why we are considering the worst case scenario. Definitely, if you are lucky, sometimes some nodes may be on the same track, etc., etc. But worst case scenario we are considering that in order to access each of the nodes in the path from the root to the leaf, you need to do one IO, which require one seek also for each node. So in order to reach to the leaf node, you need, so how much time will be required? Hi into Tt plus Ts. Tt is the time required to do the data transfer, one block transfer time, and Ts is the one seek time. So Hi number of times you are doing both the things, so Hi into Tt plus Ts. Now once you have reached to the leaf node, now you are getting the pointer to the actual data block, actual record. So you have to do one more block access to get the actual record. So that will require another block transfer and another seek. So total hi plus 1 into tt plus ts time will be required. This is the cost. So now what is happening? We are scanning actually the index, the B plus tree, to check for the equality condition. Fine. Now, let us assume that we are doing on a non-key attribute. Now, if you are doing it on a non-key attribute, but remember, this is a primary index or clustering index. Some people say that primary index and clustering index are same. Some authors, you can see that they are using two different terms, meaning they are not synonymous. Meaning primary, the difference is that in both cases, the file will be sorted based on the search key. Both cases, primary index and clustering index, the file will be sorted according to the main data file. The relation will be sorted according to the search key. However, the search key may be a candidate key or may not be a candidate key. That means there may be multiple values or may not be may not have multiple values. If it is a key attribute, then there will not be any multiple duplicate values. It will not duplicate rows, duplicate values for that particular search key attribute. So depending on that, if it is a candidate key, then we say it a primary index, otherwise it is a clustering index. And some people say that both are clustering index. Does not matter. Now the point is that the data is stored, sorted. The main relation is sorted. And you can have multiple records. So what would be the cost in this case? See, in this case also, what is the procedure? You have to first scan the index file, that means the B plus tree. and then reach the leaf node to see which record, the first record which is satisfying your condition. And then what you have to do, and then you have to access all the blocks which are containing the records satisfying that condition, selection condition. So here B denotes that number of blocks which are satisfying, number of blocks containing the matching records. Okay. So understand carefully. So first you are starting from the root of the B plus tree to the leaf. What is the cost? Hi into Tt plus Ts. As I said that Hi number of block transfers and Hi number of seeks will be required. Then you have to do one more seek to reach the first block where you are getting the first record, matching record. So one seek is required, time Ts, and then you have to only transfer the consecutive blocks, B number of blocks which are containing the matching records. But you do not need any more seeks. Why? As I have already said that now you are doing consecutive block accesses. Arm is not moved in between anywhere else. So you do not need any more seeks. So only one seek to reach the first block containing the first matching record. And then you only need the transfer. So TT into B. Up to this point, if any one of you have any doubts or questions, you may ask me. Then I'll try to explain it with more clarifications if you face any difficulty in understanding. Okay. Now we move to the next algorithm. Now suppose you have to do, you have a secondary index. You do not have a primary index. Now you have a secondary index and you have to check the equality condition, selection condition is equality condition, maybe on a key attribute or maybe on a non-key attribute. Now you have a secondary index, meaning what? That the file is not sorted. The records are not in order. The records are not in order of the search key. So what would happen in this case? If it is a candidate key, meaning the search key is a candidate key, then you will get only one record. So remember that in case of, I think you have already studied in index, that in case of secondary index, although the relation is not sorted, but the index is definitely sorted because the B plus tree is a way to access the records in an ordered fashion. So still now you will get the access, I mean, you will get the pointer to the record again with the same cost, Hi into Tt plus Ts. Once you reach the leaf node, scanning the B plus tree for that condition, you will get the record pointer. So the cost is Hi into Tt plus Ts, and then you retrieve the record. One more Tt plus Ts. You have to transfer that block. and seek the arm before reading the block, which is exactly same as the cost of A2 here, as you can see. So whether we have a primary index or secondary index, you have to check the equality condition on key attribute. The cost is same. But if you have to search equality condition on a non-key attribute, then what? Then again, you search the index B plus T. Then you reach the leaf node. So that is the cost HI into TT plus TS. Now what? Now on the leaf node, there is not a single pointer. There will be multiple pointers to multiple records satisfying the same condition. So if n is the number of matching records, then there is no other way that you have to access all those blocks containing all of those n records. And each time you have to seek the arm head to the block. So that the cost will be n into TT plus TS. Now see, that could be very much expensive. And even in some cases, the cost can be more than a linear search. Why? Why it can be more than a linear search? Think about it. Think about this by yourself. It may come in your exam. You think by yourself. Why in some cases the cost can be more than a linear search? Now, so far we were discussing about selections in the form of equality checking. However, the selection condition can be inequality checking also. For example, attribute is less than equal to some value or attribute is greater than equal to some value. Then what we should do? First option is obvious. A linear file scan you can do always. Now, if you have an index available, then what you can do? What kind of index available? Index is available. The answer depends on that. So let us first think that clustering index, primary index is available. So think about the situation first. Clustering index meaning the file is sorted according to the search key. File is sorted. Now, second thing, you decide what type of condition you are looking for. Greater than equal to or less than V. Greater than equal to V or less than equal to V. Let us first consider the first condition. Greater than equal to V. Some value is given. You have to get all the records whose value is greater than equal to V. So that means, and the file is sorted, remember. So that means you have to get the first record which is satisfying this condition greater than equal to V. And then you have to read the successive records till the end of the file. Now think about the cost. So in order to get the reference to the first record that is satisfying that condition, again, what would be the cost? You have to scan through the B plus T first. So HI into TT plus TS. And then you get the reference to the first record. One more seek will be required. And then you read the rest of the file without any more seek. But definitely block transfers will be required if B is the number of blocks satisfying that condition. Then B into TT, number of block transfers will be required. So total time will be required HI into TT plus TS plus B into TT. I think you have understood. Now for the second condition, A less than equal to V. That means you need the records where the attribute value is less than that given value. So that now this is very obvious that you have to scan the file or not scan, you have to get the records of the file from the very beginning of the file until or till the record whose value does not satisfy this condition, A less than equal to V. So clearly, then you can access the file sequentially. You do not need at all any index, or the index cannot give you any extra advantage. Now suppose you have a secondary index available, and think about the comparison conditions. Again, the same thing, greater than equal to V or less than equal to V. So think one by one. Secondary index meaning the file is not sorted. The file is not sorted. So, and greater than equal to V, you have to find. So what can you do? The file is not sorted. So you cannot take any advantage from the file, but the index, definitely the index structure B plus T is sorted. So what you can do, you can use the B plus tree to get to the first entry, which is satisfying that condition. And from there, you just access sequentially the leaf pages of the tree, because the tree leaf pages are already sorted. When you create an index, you know already that index is sorted, whether the file is sorted or not. And then the second layer, third level, fourth level, you construct the root up to the root. It is a bottom-up approach, you already know, when you construct a B plus tree. So the leaf nodes are already sorted. So you scan from the root of the tree to reach to the first leaf node, which is satisfying the condition. And then you scan the leaf nodes sequentially to get all the pointers to the records which are satisfying the condition. And then you can access the records. If you have to take the other condition, A less than equal to V, then see, in this case, you have to scan the leaf pages from the first leaf page. That means you do not have to traverse from the root. You can start from the, because we need the records, and the record pointers are already sorted. The index file, which is the sequence of record pointers, that is already sorted according to the search key. So you can start from the first leaf page up to the leaf page which is containing that condition where the condition fails. So retrieve all the pointers and then accordingly retrieve the records. Again, you can understand exactly how much would be the cost in terms of block transfers and seek that you calculate by yourself. But it is easy to understand again that most of the time the cost of this search would be even more than a linear file scan. So these were the 6 algorithms that we discussed. Again, a quick recap. The first algorithm is linear scan itself. Second algorithm, A2 to A6, all algorithms, index search, assuming some index exists. Now, what kind of index, whether it is a clustering index or secondary index, what kind of search key we're using, whether it is a candidate key or non-candidate key, and what kind of condition you are looking for. Is it an equality condition? Is it an inequality condition? Greater than equal to condition or less than equal to condition? Depending on that, different strategies exists. And you can utilize these strategies which are optimal for those conditions and existence of those indices. in terms of their cost delay. So up to this point, if you have any questions, you can ask me. Then we can move to the next topic. Is clear? Next, conjunction operation. Theta 1 and theta 2 and theta 3 dot 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 theta n. Conjunctions and operation and between multiple conditions. Theta 1, theta 2 up to theta n are conditions. Each of the condition again may be of different kinds. Maybe an equality checking on a key attribute, inequality checking on a key attribute, equality checking on a non-key attribute, etc., etc. And the attribute on which you are applying the condition, there may exist no index, there may be a primary index, there may be a secondary index. But you have to calculate the result of applying all the attributes together, meaning the conjunction, on a given relation. How can you perform this operation? What is the algorithm? It is saying what? That take any of the conditions, n number of conditions, and then check the algorithms that so far we have discussed, A1 to A6, which one is optimal? Just estimate the cost. Don't execute the algorithm, but according to the formulas that we have deduced so far, you estimate the cost of applying that particular condition theta I is equal to 1 to n. Then you choose the I with the for which you are getting the lowest cost. Then what? Then you execute that algorithm. If you execute that algorithm, then you will get into main memory the result of applying that theta I on R, sigma theta I on R with the lowest cost will be retrieved into the main memory. Then what about the other conditions? Now test the other conditions on the tuples inside the main memory only. When you have retrieved those blocks, you now apply the other conditions inside the main memory. So you do not need any more block access. Retrieve all the blocks which are satisfying theta I. Then check the other conditions on all those blocks. Which one should be theta I? As I have said, that for each I is equal to 1 to n, you can apply the formulas that have been deduced for A1 to A6 algorithms and then check for which I you are getting the optimal cost. Okay. Now here we are assuming that, meaning if that one index exists. If index does not exist, then you have only one option. You can apply only algorithm A1. But definitely when you have to apply A2 to A6, you are assuming that there exists an index. Now there are two types of indexes. I don't know whether this has been discussed also or not. Simple index and composite index. Simple index is only one attribute, and composite index meaning multiple attributes as a search key. For example, you can build an index on the roll number, or you can build that will be simple index. But if you make an index on roll, say age and CT combination, then it is a composite index. So if you have a composite index, how can you take the advantage of that while calculating the result of a conjunction? So you have to check whether whether there exists any composite index which takes all the attributes given here, meaning all the attributes involved in each of theta 1 to theta n. If it is so, then you can treat that composite index simply as a simple index and can apply the algorithms A1 to A6 to decide the formulas, with the help of the formulas, to decide which one will have the lowest cost. It's very easy. Combination of the attributes itself, you can assume as if that is one single attribute. For example, I'm just giving one example. Suppose I'm giving one example to explain this particular thing, what I said. Suppose if I have only one attribute A, then A can have values, say A1, A2, up to AN. But now if I have two attributes A1 and A2, and suppose A1 can have these values and A2 can have these values B1, B2 and B3, then you can take A1, A2 concatenation as an attribute which can have values A1, B1, comma, A1, B2, dot, 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 A1, B3, comma, A2, B1, comma, A2, B2, dot, 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 up to A and B3. So that means the value of this is an ordered pair here. Now, if you take a combination of more attributes, then it will be a tuple. So I think I could explain. If still there is any doubt, you can ask me questions. Now, next is what else you can do. Now, suppose you don't have any composite index, you have simple index available, index files available for the attributes involved in the selection conditions theta 1 to theta n. Now, what you can do, apply each of those conditions on the index file itself. Remember, not on the file, data file. Apply the conditions theta 1, suppose, to get the record pointers only, not to get the data, just get the record pointers in main memory. Similarly, apply theta 2 on R and then get a set of record pointers. Similarly, you apply dot 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 theta n on R and get the record pointers. And now all the record pointers, you just calculate the intersection of all those sets. Certainly this will give you the pointers to the intended records only. Similarly, if you have to do a disjunction operation, theta 1 or theta 2 or theta n, what you can do? Of course, one option is linear search. Another thing you can do, like in conjunction we need intersection, you can do union here, because you know AND is equivalent to intersection and OR is equivalent to union. So apply the conditions on the index file, that means the B plus tree, to get the record pointers satisfying theta 1, then get the record pointers satisfying theta 2, etc. And then calculate the union of those record pointers, and then fetch the records according to the result set of record pointers that you have obtained. But remember one point here, the difference between conjunction and disjunction. Suppose there is no index available for one particular attribute involved in theta 1 or theta 2, any one condition. Okay, what did I say? Suppose there is no index available for one particular attribute A, which is involved in the condition theta 1 or theta 2 or any theta n. Then can we apply this union technique to calculate the disjunction? No. Why? Because then those records which are satisfying theta 1, you cannot retrieve using the index search. You have to retrieve those records only by linear search. Now, if you're already doing a linear search on the file, then no need to do any other thing to check the other conditions. If you're doing a linear search, then check all the conditions that time only. However, in case of conjunction, you can take the advantage of some indices even if some indices are not available for some attributes. Why? Because as you know that this is an ended condition. So if one condition fails, then also that record will not be taken. If one of the conditions from theta 1 to theta n fails, then that record will not be taken in the result. So you can apply the available indices to filter out the records. If they do not pass theta 1, definitely they will not come in the result. Or they do not pass theta 2, so they will not come in the result. So if index is available only for suppose theta 1 and theta 2, take the advantage of only those two indices at least to filter out the records, record pointers, and fetch the records only after applying the filtration with the help of the available indices. And then check whether the other conditions are satisfied or not, but that will be an in-memory check. You do not have to do any more block access. But in case of union, you can take the advantage of union. In case of disjunction, you can take the advantage of union operation only when index is available for all the attributes involved in theta 1 through theta n. Negation is very easy. You can linear search. Linear scan is available option for any operation, whether it is selection, projection, negation, join, anything, linear search. Alternatively, what you can do, if there are only very few records available which are satisfying that negation condition, and an index is available on the attributes involving theta, then you can use that index to find the records which are satisfying the condition and fetch the records from the file. So that's all about indexing. Now the next topic that we'll discuss, next operation, is sorting. Sometimes we need to sort the data, right? In some relational algebra expression, relational queries you have seen, sorting is required. You need to display the result in a sorted order. So that is one need that you need to do sorting on that relation. Another need is there, which you will see later, that in order to perform join operation, if we perform a sorting before doing the join, then the cost of the join operation reduces considerably. Okay. If you perform a sorting on the data relation before performing a join operation, then the cost of the join operation reduces considerably. So that is another need. Why? So these are the two needs. Sometimes the user query is such that you need to display the result in a sorted order. That is the need for doing the sorting. Like you have seen maybe in the aggregation functions, etc. And second thing is internal purpose of the database system. The user query is only join, but in order to implement the join, to perform a sorting on the relation first, then the cost will be reduced. That is the purpose. How would we perform the join? Okay. Sorry. How would we perform the sorting? There are two ways of doing a sorting on a relation. First thing, if it depends on what is the size of the relation. If the file is very big and it cannot be accommodated inside the main memory, then we have to use external sort merge algorithm. However, if the relation or the file containing the relation is not that much big and it can be kept inside the main memory, then you can apply any sorting technique that you have learned in your data structures and algorithm course. Any sorting technique you apply in memory sorting and then write back the result to the disk. But suppose the file is so big that it cannot be accommodated in the main memory at the same time. Then you have to use external sort merge algorithm. Now I'll try to explain this external sort merge algorithm, how it works. It says that suppose you have m number of capital M number of blocks available in the main memory to perform this merge operation, sorting operation. You have m number of blocks available. Then what would you do? You will take the first m blocks of the relation in memory, then apply any in-memory sorting algorithm, sort it. Then create a temporary file. These are called runs. These files are called runs. Okay. Create a temporary file which are called runs. So for example, as the example is being shown here, suppose you have, let us for the time being, let us for simplicity purpose, let us assume that one block can contain only one record. Just for simplicity purpose, let us assume that one block can contain only one record. And in memory, you have only 3 blocks available to do this sorting. So what has been done here? You take the first 3 rows of the table, that is G, A, and D in memory, and then apply your sorting algorithm, any sorting algorithm, quick sort, merge sort, bubble sort, any sorting algorithm, and then to order the tuples, A comes first, then D, then G. Then this is temporarily saved in a file. So this one is the first run file. This is named as R0, run 0. Similarly, you next in this 3 blocks available in main memory, 3 pages available in main memory, you fetch the next 3 blocks, which are B, C, C, B, and D, and then you sort it. So in this way, then how many run files will be generated? So since there are how many entries? 12 entries. And for the simplicity purpose, we assume that one entry meaning one block. So there are 12 blocks in the main relation, and we have 3 blocks available in the main memory. So how many runs will be required and how many run files will be generated? That is equal to 12 by 3 is equal to 4. So 4 runs are executed, and as a result 4 run files R0, R1, R2 and R3 4 temporary files are generated. Okay. Now to do what? Now suppose I can explain it in paper and pencil better. So what are you doing? You have, this is the main memory and you have m number of blocks available here. This is block 1, block 2, 3, up to m number of blocks available in main memory to do this sorting. First step, I think you have already understood that this is the main file and you have many number of blocks here. And then accordingly, you have created run files. So this is run file 0, run file 1, and suppose you have created n number of run files. How did you create the run files up to this point? I think you have already understood. Now let us suppose this n is less than m. What would be what we would do if n is greater than m? That we'll discuss later. For the timing, let us assume that this n is less than m. That means what? The available memory has enough space to accommodate at least one block from each of the run files. The run files generated, they will also have some blocks. This is the first block of the run file 0. This is the first block of run file 1. This is the first block of run file n. Now what we would do, we would use the last block, this mth block. We would take the first block of run file 1 here. We'd take the first block of run file, the second run file here. In this way, the nth run file, the first block will take in the nth block of the available memory. So first n blocks are filled. The rest of the blocks will be used to save the output. That means rest of the m minus n blocks will be used to save the output, which should be at least 1. So I think you could understood what I'm saying. First step you have already understood that depending on the available memory, we take chunks of the main original file, which can be accommodated in the file. Then apply any in-memory sorting technique to generate these run files, which are sorted but containing portion of the data of the main file. Now what we are doing, we are assuming that the total number of runs is less than m, so that m minus n is greater than or equal to 1. That means taking one block from each run file. After taking one block from each run file, there will be at least one more block available which will be used to hold the output. Now what would you do? See, this contains in sorted order the entries from this file. This contains the data, meaning sorted order, the tuples from this file, etc., etc. So what would you do? You will compare the first entry in this block and the first entry in this block and the first entry in this block. So all the 1 to n first entries you will compare, and the smallest one you will pick and insert in the output block. Then suppose this is the smallest, then you will delete it from here, remove it from here. So this again the same process you will repeat. Again the first entry is, now the first entry of this block is this one. So again the first entries of each block you will compare, and then the smallest one you will take as the second entry in the output file. When the output block is filled, you will write it back in the disk as the first block of the updated relation, sorted relation. And in this way, when you are deleting the entries, suppose the block is empty, then you will take the next block from the corresponding run file until the file is finished. Now you can understand that this way, this will be filled with the entries in the sorted order. Any one of you, any problem or doubts in understanding up to this point, you may ask questions. Now, what we should do if n is greater than m, that means the total number of run files generated is even larger than the total number of blocks. So you cannot accommodate even at least one file, one block from each file in the memory. Then you have to, easy to guess that you have to do multiple passes. You have to execute multiple pass. So in the first pass, actually, how many files will be sorted? How many run files will be merged? Actually, m minus 1. M minus 1 file, m minus 1 run file will accommodate here, and one file will be reserved for output. So m minus 1, first m minus 1. So for example, suppose m is equal to 30 and n is equal to 100. So in the first pass, first 30 run files R0, or you can say R1 to R30 will be merged, and one temporary file will be generated, another temporary file. In the second run, our second pass, this is pass 1, and in the second pass, R31 to R60, and then R61 to R90, and then R91 to R100. So 4 passes will be required, pass 3 and pass 4, and then 4 temporary files again, R1, R12 you can say, and R22, and then R23 and R24, 4 temporary files. And then since now there are only 4 files and you have 30 number of blocks available, then you can in one go, you can sort and merge these 4 files. So now I think you have understood the complete procedure. This is the complete description of external sort merge algorithm. Any questions? Cost analysis you can check by yourself, because you have already studied algorithm analysis, so you know how to check the cost of this algorithm. Now, the next operation that we'll discuss is join operation. So first we discussed about selection operation, then we discussed about sorting, and the third operation that we'll discuss is join operation. In order to perform the join operation, many algorithms are available. For example, the listed ones. Nested loop join, this is one algorithm. Block nested loop join, indexed nested loop join, merge join, hash join. These are the options available. We'll discuss some of the algorithms, we'll not discuss all algorithms. So first one is nested loop join. See, whatever I am discussing, if I set questions from my portion, I'll set questions only the algorithms that I am discussing. Only the algorithms that I am discussing. But other algorithms, if you are interested, you can study by yourself from the book. But there will be no questions from those algorithms. This is one thing. Second thing, after today's discussion, if you face any difficulty in understanding, then tomorrow morning I'll be available in my office. My room number, you may note down, CC3 building, room number 5256, second floor. So if you face any difficulty, you can directly go and discuss with me. Go there and discuss with me. Timing is say from 11 a.m. to 1 or 1:30 p.m. I'll be available there anytime you can come. If you face any difficulty in understanding, only for this purpose, not for any other purpose. So the first algorithm that we'll discuss is nested loop join. How to perform the join operation? You are already familiar with the theta join. What is a theta join? That there is a condition theta, which is something like a selection. So how do you implement a theta join actually? What is a theta join? R is a relation, S is a relation, and this is a theta join. So as you know, this is equivalent to say R Cartesian product S first you calculate and then apply the selection condition theta on the result. So this is called theta join. Now how to perform this thing? So you can do one thing. You can take each row. This is R and this is S. So you can take the first row of R and then compare it, concatenate it, not compare, concatenate it with each row of S. That you can say tuple of R dot tuple of S, dot meaning concatenation. And then check whether this is satisfying the condition theta or not. This row after the concatenation is satisfying the condition theta or not. If it is satisfying, then take it in the result or do not take it in the result. Exactly that is written here in this algorithm. See here, if you code it, this will be this. For each tuple tier in R, then for each tuple TS in S, test the pair TR TS to see if they satisfy the join condition theta. If they do, add TR dot TS to the result. Now see, in C programming you have learned this is called a nested loop. A for loop inside another loop is called a loop inside another loop is called a nested loop. That's why the algorithm name is nested loop join. Okay. And also you have learned that the inner, meaning this loop is called the inner loop and this loop is called the outer loop. So the relation that you use in the inner loop is called the inner relation and the other one is called the outer relation. For example, here R is the usually the left hand side in when you write it in the algebra format, the relation in the left hand side you take in the outer loop and the relation in the right hand side you take in the inner loop. So those are called outer relation and inner relations. So this is the nested loop algorithm. So it is the simplest one in the sense that it is easiest to implement code. And also it does not require any indices. Any index file is not required. So that can be implemented. This can be implemented. This can be used to implement any kind of join operation on any kind of relations. It does not matter whether there exists any index or not, whether the relation is sorted or not, does not matter. You can apply in all situations. So that is the advantage of this algorithm. But the problem is that the cost is definitely much expensive than some of the other algorithms available we'll see later. But the other algorithms that are available, you cannot apply in all scenarios. As I have stated at the beginning of the discussion that in order to implement a particular operation, there may be multiple algorithms available, but you cannot say that one particular algorithm is optimal in all situations, or there is no universally optimal algorithm. One algorithm is optimal in one scenario. Other algorithms are optimal in other scenarios, etc. So each algorithm has its own advantage and disadvantages. So the algorithm, when you study some algorithms, for example, selection, you have seen 7 algorithms. Sorting, you have seen 2 algorithms or 3 algorithms. Join, you will see 1 or 2 or 3 algorithms. So when you study these algorithms, now you must compare in your brain between these algorithms. That is actually actual study, not only checking the code. Compare the algorithms. What are the relative advantages and disadvantages of the algorithms? And such type of question you can expect in the exam. So next algorithm for join is no, this is their continuing. Okay, for this nested loop join algorithm, then let us calculate the cost first. How many block transfers will be required and how many seek operations will be required. How many block transfers will be required and how many seeks will be required. See how you are doing. You are taking the first block of relation R in memory. Okay, let us first consider the worst case scenario. What is the worst case scenario here? There is that much memory available to perform this join so that you can accommodate only one block from each of the relations. One block from R, one block from S. See, this is the minimum amount of memory required, because if you do not have this much memory, at least that you can accommodate one block of R and one block of S, then definitely you cannot perform the join at all. So that is the minimum amount of memory that should be available. That is the worst case scenario. Suppose you have the minimum amount of memory available. One block to accommodate one block of R and to accommodate one block of S. So how do you perform the join then according to this algorithm? You have to take the first block of R. Then you compare the first tuple of R with all the tuples of the first block of S. Then you replace the block of S by the second block of S and do the same thing. And then you replace the second block of S by the third block of S, etc., etc. Once you reach the end of the last block of S, meaning when the last block of S is also done in that way, then what would you do? You have to again replace the last block of S by the first block of S. Why? Because then you need to compare, concatenate the second tuple of R with the first block of S. What I'm saying is, how can you perform this thing? So you have one block available. So suppose this is the first block of R that you have kept in memory. And in S, suppose there are total 3 blocks, B0, B1 and B2. And suppose these are the blocks A1, A2 and A3. So in memory, you have only one space to keep one block from R, one space to keep one block from S. So first here you take A1 and here you take B0. Then the first row you compare with all the tuples of B0. Then you replace this B0 by B1 and then replace by B2. That means up to this point you have done all these comparisons. Then you have to do what? Then you have to take the second tuple of R, and then you have to start comparing again from the first row to the last row of B1 S. That means this remains the same. You have to replace again B2 by B0, and then B1, and then B2, etc. So considering this, you tell me how many total block access and how many total seeks will be required. if BR number of blocks are there and BS number of blocks are here. So you need to access all the blocks. That means BS number of blocks for each tuple. And suppose there are NR number of tuple here. So that means NR into BS. NR into BS. These many block transfers will be required, right? And at the same time, you need to, when comparing with all the rows of A1 is done, then you have to replace A1 by A2 and then by A3. You have to read BR, this R file only once. So that means BR block access will be required. So plus BR. These many block accesses will be required, meaning block transfers will be required. NR into BS plus BR. Now, how many seeks will be required? How many arm movements will be required? Total number of arm movements is NR plus BR. Why? Why? Because see what we are doing when you are keeping the fast block here, you need to scan through this entire file. But you are scanning through this entire file contiguously, one after another. In between, you are not doing any other, you are not moving the arm into any other place. So that means if you do just one seek, then you can read the consecutive blocks. You do not need to move the arm again. So one seek is required for the first tuple. Then again for the second tuple, when you need the first block, you need to set it again at the head of the file. So in this way, since you have to access NR number of records, so that means you have to scan through this file NR number of times. And for each time you will need only one seek. So total NR number of seeks will be required to get this file. And to read this file, how many seeks will be required? If you are guessing that only one seek will be required, that is wrong. Why? Because for the first time you set the head here. As I said that if in between it is not displaced anywhere, then no more seek will be required to read the successive blocks. But what happened after reading this block, your head moved to this place. So when you want to read the second block, again you have to place the second head at the beginning of the second block. So in this way, how many seeks will be required? That depends on total number of blocks available in this relation, that is BR. So NR plus BR, these many seeks will be required. So we end at this point today's discussion. Next day will complete, next week, Wednesday, there will be only one class because Thursday and Friday are holidays. And tomorrow also it is not possible to take classes because I think you have some those products and other things. So next week, Wednesday, again, one class I'll take where I'll complete the other operations. So today's discussion, if you have any questions, any doubts, you may please ask. Otherwise, we can end the class. Okay, thank you all of you.